channel property node. If I select that property, I now have two buttons down here at the bottom to create or create right. So I can go straight to dropping that property onto my block diagram. So if I create a right property, now I've got that property node on my cursor. I can drop it on my block diagram and close my class browser. If I wire it in, and then I can just right-click and create a constant and set it to true. I've now enabled that property. If I want to check exactly what that property does, make sure that it does what I think it does, I can just use the context help and check to make sure that did what I thought it did. Wire up my error wires, just for good measure. Another nice feature of property nodes is that we can right-click on the property node and there's an option to select filter. By default, DAQmx is going to show you all the attributes for all devices. If I'm trying to go spelunking and look for a property for my specific device, I don't want to see every attribute for every old SCXI module and every single DAQ device out there. So I can either show attributes for just devices I have on my system, so that'll include anything real or simulated that I have showing up in maps, or I can choose attributes specifically for a set of devices. So right now I've got a USB X series and a USB digital card, so I'll show attributes for just those. You'll notice in the analog input and analog output sections, I've got all my properties. If I go back and change that filter, I'll only select the filter for my USB 6501 for my digital device. If I look at my properties again, you'll now notice my analog in and analog out sections are completely missing. So now I only see properties that are configurable for that device I selected. So this is great to go digging for a property that applies to your device and learn new things about your device, learn new things you can configure. So a couple things that we can do with property nodes. One of the things we do very frequently is read back coercive values from a property node. There are properties in DAQmx that, while you can set an arbitrary value, the hardware might only be capable of doing specific values. The most common example of this is sampling rate. I can set my DAQ device to an arbitrary sample rate, but that doesn't mean my device can actually support it. So I've got a standard, I've got a standard DAQmx task. I'm inputting my sample rate, and then I'm going to use a property node, the DAQmx timing property node, to read back the sampling rate that my device could actually achieve. So if I put in a nice common sampling rate like 1 kilohertz, you'll notice my actual sample rate was 1 kilohertz. That's a number I can divide down from the onboard time base. If I choose a rate that I couldn't actually divide out of my time base, if I try and use 31 kilohertz, you'll find the device isn't actually capable of generating a 31 kilohertz clock exactly. So you'll see we've generated a clock of 31 kilohertz and 7.75 hertz. So that's the closest value DAQmx could actually generate, and now I know what value is actually being used by my hardware. This is especially important for an application like analog output. If you're going to generate a buffer of data, you want to make sure that your data is generated at the rate you expected it to be. You don't want to calculate points along a sine wave at 31 kilohertz and then generate them out the front end at a slightly faster value. If you measured it back, you would see it wasn't actually the frequency you expected. So the next topic is querying properties of our hardware. So in addition to reading back the coerced value that we got, we can use a property node before we've even configured something to see what values our hardware is capable of. We can also query terminals instead of hard coding them. You can see here I'm trying to synchronize two tasks. These could be two tasks in a CDAQ chassis. These could be two PCI cards connected to a RISC, or these could be two PXI modules in the same chassis. I could, if I wanted, just right-click, create a constant, and hard code the name of where I'm going to get my start trigger from. But then if I change the name of my module in Max, or if I change what device is running on my first task, I've written a very brittle application. It's not going to work correctly after I change my name. So instead, I can drop a property node in my master task and actually read out of my master task the name of the terminal and pass that directly to my slave task. No matter what I change my first task to use, that will always spit out the value and pass it into my slave task. I've now written it to be much more robust across changes to my hardware. Like I said, we can query properties of our device. So I'm going to drop a property node in order to help me decide what sample rate I should set my AI task to. So I'm going to go grab a property node from the class browser, so go to View, Class Browser, and I'm going to search for maximum rate. So I want to find the analog input maximum rate. So you can see here, there's a couple different properties to choose from, but if I drop down, I'm sorry, I want a read version of the property node. I think I've grabbed the wrong one. I'm going to just use quick drop and drop a DAQmx timing property node. Wire it in. I know what I've done. My filter is still set to the digital device, so I'm going to go back to showing all attributes. I want sample clock and then maximum rate. So when I read from that property, I'm going to take into account all of the other settings I've configured for my task, and it's going to spit out the maximum rate that I can achieve based on those settings. So this will take into account what device I'm on, and how many channels are in my task, and actually calculate out the rate I can use. So I'm going to delete my sample rate control from the front panel and wire that up. So if I run this for a single channel, you'll notice I get a nice fast rate. I get 2 megasamples a second. Yes, sir.
So if, for example, if your task has multiple channels across multiple, let's say, different CDAQ modules, let's say 9234, which is a 51,200 sample rate, and a 9213, which is 75 samples per second. Which rate are you getting if you've got a task that has both channels?
So the second module you listed was kind of a special case, in that it's a slow sample modules. Those have some special behavior when you use them in a task with a faster rate module. We could use an example like a 9205 and your 9234, where they're both fast sample modules. In that case, we will consider both modules and give you the rate that they could actually both run at. So if you have...
And so what's the special case? Because my customer application is a combination of 9211s, 9213s, and 34s.
So the special case for those slow sample modules is that those will return repeated data at a faster rate when you put them in a task with a faster module. So there's a nice white paper that if you search for CDAQ slow sample modules, it'll talk about how it chooses what rate it's going to run at. So if I now change to 2 channels in my task, you'll see my rate's going to drop to 500 kilosamples a second. If I change to 4 channels, it's going to drop even further, 200 kilosamples a second. So now my application, however many channels I put in my task, whatever device I run my task on, is just going to run at the max rate that hardware can handle. And that's certainly not the only property that we can do that with. That's just one that I use pretty frequently. So now that we're using property nodes a little more effectively, we also want to think about how efficiently we're using them. Both of these sets of property nodes accomplish the exact same thing. They set 4 timing properties, and then they read back those properties to see what values they got set to. They will both run, they will both give you the same result, but which one of them will run more efficiently? So the one on the right looks nice. We're setting a property and then we're immediately getting that property back. If you've never read it before, there's an excellent topic in the DAQmx help file on the DAQmx task state model. As you take a task from configuring the task all the way up through running it, there's different phases that we go through. One of those phases is verifying all of the configuration for the task. In order to read back from a property node, we have to verify all of the settings for your task, not just that one setting, to ensure that no settings conflict with each other. If you set a channel type that's not available, that precludes a certain trigger type, we need to check all of your properties against each other. So every time that you set a new property, we undo that verification and we'll have to do it again. So by setting all of our settings up front, before we read back any of them, we only have to verify once. On the right, we have to verify 4 separate times every time we read back from one of our properties. Yes, sir? So by default, LabVIEW is going to just execute property nodes in the order you've set them.
And they're kind of unique.
Right. There are times where you may need to set one property before you read back or set another property. So the next topic is DAQmx TDMS logging. Many of you may have used TDMS files before, but I've found many customers aren't aware that a DAQmx task will log directly to the TDMS file. No need for you to set up a producer-consumer or use the ExpressVI to log the file. You can drop down the DAQmx configure TDMS logging, pass it a file path, and we will stream data directly to that file. The TDMS file type has some special features that when we use it with DAQmx, we actually hold the raw data from your device straight as it comes off the ADC, not scaled, not calibrated. We dump that raw data into the file, and then we dump the scaling information and the calibration information into the file. So when you choose the log option, the data is streamed directly from your device to the disk. It doesn't come into LabVIEW. DAQmx doesn't have to spend any effort scaling it. So it's tremendously efficient compared to the standard producer-consumer. So some of the metadata that we store automatically, we store the unit for every channel, we store the initial timestamp, we store the time between samples, 1 over your sample rate, and we store the names of all your channels, or if you haven't set the name, we store the physical channel name. So I'll show you. Here I've got a simple analog input application. I configure my channel, I set up my sample clock, and then I use the TDMS logging VI to give a file path. I've set it to log, and I can also control if we create or replace the file. I start my task, and then inside the loop, I'm not even reading the data back. It's going directly to the file without ever coming into LabVIEW. Then at the end, I've got an especially useful VI. It's the TDMS file viewer. This opens up a separate window where I can look at all the data in my TDMS file. So once I've finished with my acquisition, I'm going to pop that up so we can take a look at the data. Yes, sir?
What is the stop that closes the file?
So the file closes when you call DAQmx stop. So I can run my acquisition. I don't have anything connected, so we'll see floating data. But I can go ahead and stop. And then the TDMS file viewer is open. Yes, ma'am?
Can you leave it at the sign down?
So you can. There are caveats. You want to make sure that you're trying to that you're using the low-level TDMS files to TDMS file VIs to open it. If you try and open it with the ExpressVI, it'll take exclusive control of the file.
Sorry, when you say low level, do you mean like the standard read or open and close, or do you mean the advanced open and close? Or you just mean not TDM or not Express?
Definitely not the ExpressVI. I honestly haven't tried it with the standard open and close. I've just typically used the advanced.
Okay. And then I have one more question. Can you, if you have like 2 DAQ tasks, can you stream them both to the same TDMS file at the same time?
No. So the DAQmx TDMS streaming streams to 1 file per task. You can't merge 2 files into the same task.
I want 2 tasks into the same
I'm sorry,
file.
you can't merge 2 tasks into 1 file.
Okay.
So by viewing the file, are you affecting the sample rate?
By viewing the file,
If you're viewing the data as it's, your example, you're just saving directly to disk. If
Right.
you view it as it's collecting, are you affecting the sample rate?
you're not affecting the sample rate directly. The sample rate is running according to the clock on the device. you are affecting the rate that the bandwidth you could achieve effectively, because now DAQmx does have to scale it and display it to you in LabVIEW. So the streaming's still going on behind the scenes, but we're also doing a standard read on top of it. I would have to set it. I would have to set it to log and read, not to just log. If I set it to just log. Yes, ma'am.
Do you require a lower sample rate to display at the same time?
Not directly, no. So here I've got my TDMS file viewer. I can see the different channels I had in my task, and here's all their metadata. And then I can view the values as a table or the values as a graph. The other very common thing is to open the file in Excel. So with the TDMS plugin for Excel, I can just double click on that TDMS file and it will open in Excel. All of my same metadata is here, and all of my numeric data is visible on the second tab. One of the other features that's very useful is the Start New File VI. So if you're running a long acquisition, you can use this to split up your files so you don't end up with one file for your entire acquisition. You can set it up to do this every so many minutes or every so many hours. You control it because you put that VI in a loop. So you can use that to generate a new file. Another thing to keep in mind is that the metadata for the timestamp and your time between samples is based on the settings of the DAQ task. If you use an external sample clock, or if you don't actually use a clock at the rate you've configured, the metadata reflects the settings of your task. It's not measured from your actual clock. So next we have I/O name filtering and using internal channels on your DAQ device. So by default, when you click on a control for a physical channel or a terminal in DAQmx, we're only showing you part of the picture. We're only showing you the most common terminals and channels that are available to standard users. There are many more items available for an advanced user if you know how to get to them. So we can take any, I'm sorry, I want to manual again. So on a standard physical channel control, I can right click on that control and select I/O name filtering. Let me close out context. And you'll notice here's a checkbox for internal channels. So checking this box will show you all of the internal routes that are available for specialty use on the device. There's some other useful features here. We can limit that control to a specific device or to a group of devices. So if I have many different DAQ devices on my system, but I only want a user to select a certain device from this control, we can limit it to that device. It's just a standard drop-down. So we can set which device is available through that control. And this is how you can go in and change the I/O type for that control. All of the controls, all of the physical channel controls in DAQmx are the same. They just have different filtering applied. So if we change it from analog input to analog output, and I hit OK, now you'll see even though it's wired to an analog in task, I only get the analog output item. So it's decoupled from the actual VI you're using. It's just based on the filtering that's configured. And I would certainly never condone such a thing. But if you open up the actual DAQmx VI, all that we have is a filter applied there. And it's in memory, so it's not going to let me, but you can go in and change that on the actual DAQmx VI on the palette. That would be a terrible thing to do to your coworkers, and I would never condone such a thing. I can not directly. So now when I open this drop down, and let me set it back to normal. Now when I open the drop down, in addition to my standard AI channels, I've got these specialty channels. So I can read AI ground with respect to AI ground. we should all expect to get right around 0 volts when we measure that, right? That's a good diagnostic channel to use. I can also use my analog input to measure what's happening on my analog output. So here I have AO0 versus AO ground, AO1, AO2, AO3, etc. There's also another fun one, is the board temperature sensor versus AI ground. It's the last option. This will usually read out in 10 millivolts per degree C, but you would have to check the DAQmx documentation for your specific device. Some of the older devices don't use that scale. But then we can read out the actual temperature of the onboard sensor on your DAQ device. On a terminal, here you can see I've got my PFI lines, I've got some time bases, I've got my AI and AO start triggers, but then, and I've already enabled, I'll go ahead and show you. If I do ion name filtering and I include advanced terminals, we have specialty terminals for routing things internally within the timing chip on board your device. So if I scroll down, all of these specialty counter terminals are hidden by default, but if you enable internal channels and advanced terminals, we can see the most common one we use is to internally route the output of one of your counters. So if you take one of your device's 4 counters and you use it to generate a clock, we can use these advanced terminals to route that clock to be used as your AI simple clock. Or we can route that out to another counter. We can use this to cascade counters. If you need to count some particularly fast signal, we can route the output of one counter to another counter and effectively have a 64-bit counter instead of a 32-bit counter. So you'll see I'll use these internal channels throughout the rest of the demos. Excuse me.
For analog outputs, is there a neutral channel established?
You're getting a little bit ahead of me, but that particular feature is only on a small subset of devices. We've got some similar features that I'll show in a bit that are available on a wider range of devices. So here you can see those same options are available on constants on your block diagram. They're not just available on front panel controls. So another feature that many people may have seen but have never been sure how it's used or what it can do is the frequency output, or in much of the documentation it's freak out for short. So this is a low-featured counter that's independent from the main counters on your device. We can take in a time base, the 20 megahertz, 10 megahertz, or 100 kilohertz, and then select a divide down to 1 to 16. So this effectively gives us a range of around 6 kilohertz up to 20 megahertz. We don't have the same level of control we do with a typical counter task. We can't set it to be finite. We can just start it and let it run. This is especially useful on the M-series devices, where the digital I/O subsystem didn't have its own timing engine, so you had to provide an external clock. Many people piggyback it off from one of the analog clocks or use one of the onboard counters to generate a clock. But you can also use the frequency output to generate a clock without using one of your regular counters. Another thing we can do with this is use it as a trigger. Many people don't think to use it as a trigger because it's a pulse train, not a single pulse. But we're just looking for the first edge, so it doesn't really matter in most use cases if we continue to toggle that line after we've received our trigger. So next we'll talk about digital filtering. You can see here, if any of you have seen in previous NIWeeks, we had a Mr. Potato Head laser scanner. This was set up, there's a motor that spins the platform underneath Mr. Potato Head. And then on the right of the image you can see we have a laser distance sensor that scans the radius of Mr. Potato Head as he rotates. That laser sensor moves up and down so that we can cover the entire surface of Mr. Potato Head and get a 3D map of his volume. So in order to ensure that we took analog samples at a consistent angle around Mr. Potato Head, we have an encoder attached to that platform. That's all well and good. That gives us a digital edge at every degree in this case. But right underneath that encoder is a DC motor running that platform, spinning that platform rather quickly. So that meant our digital signal was very, very noisy. We had lots of glitches, and since we were trying to drive the analog sample clock of our device with that glitchy signal, we ran into overrun errors. So if we provide a clock edge to the analog sample clock, and then we provide another clock edge before that sample had finished being acquired, we're going to get an error. We tried to clock the ADC before it was ready. So we had to get rid of those glitches. We had to clean up our clock. The way we did that was with digital filtering. We'll talk in a minute about how it's implemented. Some other uses for it, we can also debounce a mechanical switch. So if you just take a standard mechanical switch, it's nice to think of it as a straight off to straight on, but it's never that simple. As you depress the mechanical switch, it's going to bounce a little bit. And so when we read its output, it's going to have many, many pulses instead of a single clean rising edge. Another trick we can use digital filtering for is applying a delay to a trigger. If we've got some physical phenomenon coming from an external device and we're trying to respond to a trigger, if our phenomenon doesn't happen exactly when the trigger occurs but really happens a few milliseconds later, we don't want to trigger on the edge, we want to trigger that many milliseconds after the trigger actually arrived. Usually people throw a counter at it, but counters are a precious resource. We don't want to use one of the standard counters unless we really need to. I can apply a digital filter, and that will effectively delay my signal. So here I've got I just took the standard count edges example. I've added the digital filtering property nodes to it. So you can see I configure what terminal I'm going to count edges on. I enable the digital filter, and then I set the minimum pulse width. That's the width of a pulse that will get propagated through to the rest of my device. Any pulses shorter than that will be rejected. Any pulses longer than that will be transferred through. So if I've just got a joystick here with a big red button on it. I've got it wired up to PFI 8. So when I start my task, if I depress the button, I didn't exactly get one count, did I? What's really fun is when I let go of the button, it usually bounces again. So I definitely don't want to count when the button gets released. So I can enable my digital filter, and I can configure the pulse width. If I start with a pulse width of 150 microseconds, we'll start counting over again. Now when I press, sometimes I'll get one, sometimes I'll still get a couple. I've configured a width that rejects most of my glitches, but some of the longer glitches still make it through. So you have to choose the width of your filter carefully to make sure that you're rejecting all of the unwanted glitches without setting it to be so aggressive that it rejects signals you're actually interested in. So I've experimented with it, and 500 microhertz, or 500 microseconds is about the right amount of time that I very reliably get exactly one tick every time I depress my button. So you'll notice with this one, as with many other examples, I read back my actual minimum pulse width. Certain devices only support a couple pulse widths. This device is very configurable, so it allows many, many different pulse widths. Other devices only have 3 or 4 pulse widths that you can use. So it's always good to read it back and make sure that you're actually using the value you expected you were using. So here's a little bit of the explanation of how digital filtering is implemented on our devices. We take the input signal as it arrives at your pin, and we're going to sample it according to what we call the filter clock. So the filter clock is these dashed vertical lines. Every vertical line, every filter clock, we're going to sample your input signal. So the first sample we were low, second sample we sampled high. What we need is for the input signal to sample in the same state for multiple consecutive edges before we'll actually propagate it and pass it through. In this example, we use 2. So you can see here, the first time that our input signal has actually stayed high for 2 consecutive edges is here. As soon as it has stayed high for those 2 consecutive edges, you'll notice that our internal filtered copy of the signal has now gone high. If we look at the falling edge, there was a glitch on our signal. That glitch didn't propagate. We sampled it high, sampled it high, sampled it low, sampled it low. After we had sampled it low for 2 filter clocks, we propagated that transition. So this allows us to reject those glitches, those errant pulses, but still pass through the desired signal. It does introduce a delay. You can see from the first time that we went high to the actual time our filtered signal went high was delayed by the amount of our filter clock, or by the number of pulses of our filter clock. So this is usually thought of as a disadvantage, but we can use it when our goal is to apply a delay to a signal.
And the filter clock was the thing that you made 500 or 5 microseconds, whatever it was.
So DAQmx calculates the number of consecutive samples based on that time in seconds that I specified. So I specified 150 microseconds. DAQmx said I'm going to use the 20 megahertz time base or the 100 megahertz time base, and calculated that comes out to n of 57 ticks.
Okay.
So
those filter times is your 100 megahertz.
yes, the 100 megahertz clock on the right. So now we've got some cool features for analog output. The first one is doing variable rate analog output. Normally you think of a task, you set up your sample rate, you write some data into the buffer, and then you start clocking it out, and you don't mess with it from that point on. A little known feature is that we can update that clock rate on the fly. So after our task is already running, we've already got data in the buffer, and we're clocking it out, we can use the timing property node sample clock rate to actually update the sample clock running on your device to a new rate and continue clocking out the data at that new rate. So you can see here, I loaded one cycle of a sine wave onto my buffer. I started it at a slow sample rate, then just in a loop I kept calling that property to up the rate faster and faster and faster. I accomplished a swept sine only writing into my buffer once, just by updating the rate that I was generating those data points out at. Yes, sir.
How about glitching? How is it controlled glitching when you this?
So DAQmx our DAQ devices actually use two sets of registers for the timing engine, such that we write into one register and then switch to that register on the next cycle, so we won't get a partial sample clock pulse. We will go cleanly from one rate to the next rate. On our newest devices, on X series, this is also available for analog input and digital input and output.
Does this mean that if you've got it set for a really slow rate, you'll get at least one cycle of that rate before the switch?
You will get one sample clock of that rate before you switch.
A sample?
It's not tied.
Okay.
The timing engine doesn't know what a period of your signal looks like. So it waits until the next full sample clock. And then we can pair this with onboard regeneration. That way we load our signal onto the buffer once, and we continue to generate it, and we don't have to waste bus traffic, and we don't have to waste energy recalculating our signal. We can just continue clocking it out at new rates. So I've just got my basic analog output example, and I've got some space here to add in a property node. So I want to add it in over here. So I'm configuring my analog output task. I'm setting my sample clock rate, and then I've enabled using only onboard memory. I'm generating one period of a sine wave and loading that into my buffer. Then when I start my task, I'll use a timing property node. And I want to set it to sample clock rate. I'll just make a new control. Let's make sure I set that to something reasonable before I start it. It'll get a little cranky if I try and set it to 0 hertz to output. So I've got just an analog input example here, and you'll notice I've set it to read my analog output channel with respect to AO ground. So this way I can see that my AO is working the way I expect without actually wiring anything up. I'll start this guy. output, you'll notice my sample clock rate was very low. I can increase it if I put num lock on. And so I can change the sample clock rate on the fly. I'm not writing to my buffer anymore. I'm just changing the rate at which it's actually being output. I'm just changing the clock rate that the digital to analog converter is running at. And you can check the code. I only wrote into my buffer once. I just updated that one property inside that loop. The next trick is using an analog external reference. So on board the device, we have a 10-volt reference that we use to drive the analog output circuit. Many of our devices have the option to bring in an external reference instead of just using that reference. So if you're trying to output a particularly small signal, if we take just 100 millivolt sine wave as an example, if I output a 100 millivolt sine wave on my 10-volt range, I'm using, what, 1% of my available range? I'm going to get a much choppier signal. I'm going to get much lower resolution than I could be achieving. So I can bring in an external reference at a voltage of my choosing and use that to actually drive the reference of my digital to analog converter on board the device. So we actually take that pin through, we take the external reference pin through a mux, we buffer it, and then we pass it straight to the digital to analog converter. So in analog hardware, we're applying this reference. I can do cool tricks in addition to just using it to get better resolution on a low amplitude signal. No one said it had to be a DC signal, right? If I use a reference that's changing, I can actually window my AO or modulate my AO. Yes, sir?
I didn't understand how bringing referencing in helps you when you've got a very small.
When I'm doing a small output.
Yeah.
So if I'm doing a sine wave of 100 millivolts,
Yeah.
on a 10-volt range, that's, I think I ran the math, was 600 different levels.
Yeah.
So if I bring in a reference of 100 millivolts, now I'm using all 16 bits of my output. So now I can achieve much better granularity because I'm applying those 65,000 discrete levels over just the range I'm interested in.
So you're changing the output, right? You're changing the output range of AO.
Yes. I'm actually using an external signal as the limits, as the rails for my analog output circuit. So we can set the source, so we do the AO DAQ reference source, either to external or internal. If we set it to internal, then I have just a 10 volt or 5 volt on some device internal references. If I set it to external, I have to tell it what pin I'm bringing it in on. In this case, I'm using a pin called APFI0. It's the analog PFI line. Some devices have one, some devices have multiple. And then I need to tell DAQmx what voltage level that reference is at so that we can scale the data properly before we pass it out. If I configure a 1 volt reference, I can't output 2 volts, can I? So DAQmx needs to know what you're using as your reference so that we can scale the data before we pass it to the ADC. I'm sorry, to the DAC. Do keep in mind that accuracy degrades as you increase the frequency of your reference signal. Swinging the reference of your digital to analog converter around at hundreds of kilohertz is going to have a meaningful effect on the performance we can get out of the converter. So this was just something I set up at my desk. I took one channel as a 10 hertz sine wave, one channel as a 1 hertz sine wave, and I used the 1 hertz sine wave as the reference for my other signal, and that's what I got out at the pin. Yes, sir?
How low can you go? And how do you tell which device is
So if you check your device specifications or your device pinout, the easiest way is to look at the pinout. If you have an APFI line, then it's almost definitely supported. You can check your specifications document, and it will have a line item for analog output external reference, and it'll usually say like the acceptable range is plus or minus 11 volts. That, I don't have a good answer for you. It would be hard to recommend. Yes, sir.
It doesn't actually care that your analog voltage matches what you're saying, right?
It doesn't care that it matches what I've set here,
Yeah.
because this is just used to scale the data.
Right.
So if I set an analog reference of 1 volt, and I try and program a 1 volt output, I need to set my digital value to full scale so that my analog to digital converter, my digital to analog converter passes out a full scale value that I know should be 1 volt. So this is used for scaling the data that you write to the task to the correct thing for the DAC. You're right, it doesn't strictly have to match exactly what it is, but your results will be scaled by that amount.
So if I say I'm putting in 1 volt, I'm actually putting in 10,
Mm-hmm.
then if I say I'm going to call out and 10 volts out.
Mm-hmm. Because you have to think of it as, we use this to calculate from the value you specified to what digital value to program the DAC to. So if you lie to us on one side, you'll get the result of that back out. So if I go back to my same example, and in the sake of time, I want you guys to have some time for questions, so I'll skip to the already finished copy. So here I've added in the property node for the DAQmx channel, and I've set the source to external, the reference to the APFI line, and then my reference value to 10 volts. If I open up I'm just going to open up a test panel. I've got analog output channel 1 wired back to that APFI pin. I'm going to open up an analog output test panel. Set it to A01. So if I set my analog output to 10 volts, I've just updated it. Here I'll run my analog input channel just to show you that it's working. I've got scaling turned off. When I run my output is configured for a sine wave of plus or minus 1 volt. I configured it for an external reference of 10 volts and actually provided an external reference of 10 volts. So what do we expect that we'll see from the analog input? We should see 1 volt. Now if I go and I change what I'm actually providing as a reference, if I set it to 5 volts, now we should see our analog input is reading half a volt sine wave now. Because I've lied to DAQmx about what value I was actually providing to the external reference. My full scale value is now half a volt. I can update it again. I can do if I do a quarter volt, I'm now getting a measly little quarter volt sine wave. So there is a limit of 11 volts for this device. The max external range you can use is 11 volts for this device.
I mean, even though you're not actually driving it, you'd be driving it to...
I would be driving the reference pin to 20 volts. And that would exceed the spec of that pin. Yeah. Yep. So the last feature that we'll use in conjunction with this is that I can actually mix hardware timing and software timing for analog output. On a given device, you can only have one hardware timed or one clocked analog output task running at a time. You can choose what channels are in that task, but you can't have two separate clocked AO tasks running at the same time. There's only one analog output timing engine to drive them. What I can do, though, is while that's running, I can do a software timed task on any of the other channels. So while I'm clocking out a sine wave on AI0, I can use an on-demand or software-timed DAQmx task to update the values of my other channels. So this is useful for when some of your channels are a waveform, but other channels are just a DC level or a slowly changing set point, where the exact time that transitions isn't as important. We can use the software time task to update those levels. So we're not constantly writing a waveform of a DC level. We can just update that on the fly when we need to update that one channel. So we don't waste resources calculating a channel of all 3 volts, and we don't need to waste bus traffic sending it down to our device. It also has the advantage that it will, in most cases, update more quickly. If I do a software timed update to my channel, that will happen within a couple milliseconds typically. Whereas if I if I have a waveform that I output of 5 volts, and I change my next buffer right to 3 volts, I have to generate out the entire buffer that's existing before I get to my update. So in many cases, this will actually update more quickly and more responsively than if you did all of your channels hardware time. So here's my full, you've watched it grow over time, here's my full analog output application. I've configured my device to use just the onboard memory, so I write my single period of a sine wave into my buffer, and then it's going to stay there and regenerate. I've set my external reference to the analog PFI line. I write in my 1 cycle of my sine wave, and then you'll notice down here I have a completely independent AO task running on channel 1. So channel 0 is running my hardware time task. Channel 1, because I don't have the timing VI, it's going to be a software time on-demand task. Every time I call write, it's going to update that value. So if I pull open my analog input and have it running, oh, I didn't start my other VI.
The test panel.
So should the test panel actually stop me from running that? That test panel only tries to run when I click update from that guy. I can go ahead and close it, and I've actually already closed it. Max is open, but there wasn't a test panel open. So my AI is still running over here. And now I have an AO application. So I've configured my hardware time task on AO0 and a software time task on AO1. I can now change my sample rate and my level completely on the fly. So I'm not changing the data that's in the buffer, I'm just changing properties of my device that affect how it gets generated. So that is my last slide, my last cool tip for you. Hopefully you've learned something new that you can take home and apply. And I'll be up here for a while to take any questions that you guys have. Thank you all for coming.